Well, scientists, imagine you have a coin and you want to flip this coin 100 times. You want to flip this coin 100 times. How many heads and how many tails do you expect to see? Well, you know that the chance of having heads or tails is 50-50%. Then you expect 50 tails and 50 heads, right? But what if instead of that, you actually get 49 and 51? Does that mean there's something wrong with the coin? Well, it doesn't necessarily. This variation of one, it could be just random, right? Sometimes things are not exactly 50-50. It's okay if it's 49 and 51. But what if you get 48 and 52? Well, that seems reasonable as well. Doesn't seem like there's something wrong with a coin. It's fine, it's just 48 and 52. But what if it's 47 and 53? What if it's 40 and 60? What if it's 10 and 90? How do you know when this variation you see is just random? Or is it because the distribution here is not really 50-50? How can you tell the difference? Well, you can tell the difference with a tool called chi-square test. Chi-square. For my Greek-speaking friends who are listening to this video, this is actually the chi-square test because of the letter chi, and we represent with a chi squared. This is not an x, this is Greek letter chi. So let's say you flip the coins and you actually got 47 tails and 53 heads. This is the value you actually got. I'm going to cross out the other ones. Those are not what you got. You got really 47 and 53. So this is in blue here. This is what you observed, but you were expecting here in yellow 50-50. So the first thing you are going to do is you're going to create a table. Here you have what you observed in blue, observed what you expected, and what you had. Heads and tails. Beautiful. What did I observe here for heads? 53. And for tails, I observed 47. I was expecting 50 for each. Now, what we're going to do is we are going to compare the difference between what you expected and what you observed. So here, you're going to do observed minus expected. So 53 minus 50, that's 3. And 47 minus 50, that's negative 3. Now, what you want to do is add all the differences together. Now, the problem is if you add 3 and negative 3, they're going to cancel each other out and you end up with 0. So, we are going to square the difference so this negative turns into a positive and we can add everything. This is where the name chi-squared comes from because you're going to square the difference. Now, this is not some x you have to take the square root of. This is the actual value. This is the name of the variable. It's chi-squared. Like the name of the statistic is chi-squared. You are not going to take the square root of anything. It's just a reminder that you have to take this difference here and square it so you can add them all together. So 3 squared, it's 9. And negative 3 squared, it's also 9, right? Because negative with negative turns into a positive. But now we have another situation. A difference of 3 in 100, it's not the same thing as a difference of 3 in 1,000, right? If you get €1 discount on your coffee, that's a lot. But if you get €1 discount on a computer, that's not that much. So you have to compare the difference with what you were expecting. 3 in 50 has a different meaning than 3 in 1,000. So let's compare it. How do we compare? We divide by what you are expecting. So you have here the observed minus the expected divided by what you expected. Divide this by what you were expecting. And 9 divided by 50 is 0.18. So 0.18 here, same thing on this side, 0.18. Now you are going to add all these values together and you end up with 0.36. This is your chi-square statistic. This is your chi-square statistic, right? Again, you are not going to take the square root and find x or anything. This is it. This is the number you are looking for. The name of the statistic is chi-squared, and the value in this case is 0.36. So you look at me and say, well, what does that even mean? Like 0.36, does that mean the coin isn't fair, or is it just random? Well, you have to look at the chi-square table. So here we have the chi-square table, and we are looking for how many degrees of freedom we have. And usually is going to be the number of categories minus 1. Why is that? So how many categories do we have? We have the heads and we have tails. We have 2 categories. 2 minus 1 equals 1. Why is that? Why minus 1? Why not just the number of categories? Because if I threw 100 times, if I flipped the coin 100 times, I can choose one of these categories. I can choose the number in here in one of those categories, and the other one has to be the remainder. I have 100 flips, 53. I can choose any number here. Let's choose 53 for the heads. Well, then the tails have to be 47. I can come up with 53 and 53 because that will not add up to 100. Like, I do not have the freedom to choose twice. I have the freedom to choose once. That's my degree of freedom. What if we flipped the coin 100 times and we had 10 tails? Then automatically the number of heads would be 90. We cannot choose any other number. What if we flipped the coin and we got 40 tails? How many heads do we have? 60, right? We don't have the choice here because the total has to add up correctly. So the number of categories minus 1, we have 1 degree of freedom here in this case. So you're going to look at the chi-square table. You're going to look for the line where it says degrees of freedom 1, and you are going to look for the critical value. Critical value. Right? This is the number that if your chi-square value is larger than the critical value, you have to reject the hypothesis that the difference you see is random. Okay? You have to reject the hypothesis that the coin is fair. You have to reject the hypothesis that actually the values, the expected values, are close to what you observe. What you observed is actually something different from the expected. This is not random. There's something going on that is causing the difference. If you think about it, if your chi-square is smaller than the critical value, that means the difference here, because the chi-square, it comes from the difference. That means the difference is not very big. The difference is not very big. So if the chi-square number is smaller than the critical value, that means the difference is not very big. It's just random. That's fine, right? You can keep your hypothesis that this is the real distribution. But if the chi-square value is larger than the critical value, that means the difference is too big. The difference is too big. Your coin is not fair, or this distribution here that you expected is not what is really going on. So for a critical value of 0.05, a 0.05, look at the column that says 0.05. So when you look at your chi-square table and you look at the row for 1 degree of freedom and the column for 0.05, you discover that the critical value here would be 3.84. 3.84. If your chi-square value is larger than 3.84, then you reject your expected values. You reject that this distribution you see is just random. Now let's compare. Is 0.36 larger than 3.84? No, it's not. That means, hooray, your coin passed the test. Your coin passed the test. That means this distribution you see here is just random. The distribution is random and the expected values are totally fine. Your coin is fair with a 95% interval of confidence. That means with 95% certainty of your results, with 95% interval of confidence, you know that your coin is fair and the distribution here is really 50-50. This difference here you see is just random.